So I actually don't have an anecdote of the first time I was exposed to Nobel mathematics for the only reason that I was born into it. And so I went into mathematics, academically I was born into it, when I was completely immersed in Nobel's point of view and tastes, and it permeates every single research activity I have every day since then. So there is no story, because there was never a beginning. What did happen when I met Nobel in person was, of course I was impressed, but that's kind of a banal thing to say. What really happened, because I've seen him before in action in Israel, in seminars, whatever, activities, but what really happened is that I gained what I consider a very good friend, and there are many great mathematicians in the world. When you know they're in town, you're about to meet them, you have your 5 problems that you really urgently want to discuss with them, and there's a very, very small number of mathematicians where what you really want to do is just hang out with them, and you don't care. Okay, so even though we have those 5 problems, that's how I feel whenever I meet Nova. And so I honestly know, I don't know what 60 means. Maybe in a month we can discuss it, but for me, Nova is just one of the guys that I'm happy to be here to celebrate his birthday and just talk about math. So what I'm going to be discussing today is a very central problem in metric geometry, kind of a workhorse of metric geometry. It underlies a big percentage of all papers being written, somewhere in the middle of lemmas. And what I'm going to show is a very small but conceptually meaningful progress on one of the 2 or 3 main questions in the area. But I want to start with just explaining it. It's very simple to explain because it's so general. So the situation is it's a general problem. You're given 2 metric spaces and some subset, and you associate to this triple, the subset S, X, and Y, these are the 2 metric spaces, a number. It's the smallest case such whenever you give me a mapping that assigns to a point in the subset some point in the metric space Y, you can extend it, so this is just the condition that it extends, and the Lifschitz constant of the extended mapping is at most what you're hoping for a small constant, but whatever constant you can get times the initial Lifschitz constant. So this number is the smallest scale that you can do for which you can solve this problem. Very simple to explain, and the picture is you're given a subset, you have a function, and you want to somehow extend it while hoping that the new function can be as smooth as possible, given the smoothness of f. So if f is the small Lifschitz constant, so should be f. Now, we're going to really be discussing, I chose a topic which is very discrete, and these subsets are going to be finite in our situation. So this looks like an easy problem, but it's actually a very subtle problem. It depends on the entire geometry of this triple, the way S sits in X, and how they relate to Y. And so just so you keep in mind that this is a subtle question, let me just show you just one example of an impossibility result which is recent. So here is a bad situation. So extension isn't obvious at all. You can find 2 Banach spaces, a 1net, so a maximum 1 epsilon separated subset in X, a 1 Lifschitz function from this discrete net in the set, so that any function that extended is not only not Lifschitz, it's not even uniformly continuous. Okay, so it's very subtle to extend functions, even from very discrete situations. Now, this is something I'm going to talk about a little bit later, because it's something that came up actually for this talk in some sense. You can do a version of this, so in this talk we're going to really focus on Y being a Banach space. Essentially, many of the theorems work when Y is a manifold with certain curvature conditions, and we actually care and use these things. But if Y is a Banach space, you can do a version of this question where you want the extension to take values in the convex hull of the image of the initial function at left. And let's just call the associate parameter E, the extension parameter, but with the restriction that you're inside the convex hull. And I'm going to get back to this later. But that's a variant of this question. Not clear at all that they're different. Wasn't clear to me until last week, but we'll see. But this is a variant of this question. So there are the basic extension parameters. So in this picture, what we most often want to know is we really care about the 2 metric spaces X and Y, and not really the subset. We want a theorem that says for every subset S of X and for every function F, you can extend it. So the way you do that is you just define the parameter, just depends on somehow the way the geometries of X and Y interact with each other. Take the biggest possible extension parameter of all possible subsets, no matter how crazy they are. So there are situations where this is finite and this is a magical situation. It's a very useful fact. There are rare theorems, but I'll show you some of them. Most often, this is infinite, and then the way to quantify how infinite it is, there is actually more than one way, but a natural way to quantify it is to just take the same thing, but over all endpoint subsets. So E sub n xy, let's say if it's 100, it says, whenever you give me n points in x, and a way to assign from every one of those endpoints a point in y, if it's one Lifschitz, and you can extend it in a way such that the extended function is 100 Lifschitz. Okay? Also, that was already before in my definition. Here I said for every function. That was already before. So saying that this number is 100, let's say here, it says that every subset in every function. Okay. So just so you see, so there are many, many beautiful theorems already proved, and just so an example of a question, one of the main open questions which has applications that I'm not going to discuss today, but you can see, we don't even know what happens. Is this, we do not know if it's a very old question that many people look at whether from Hilbert space to L1, this number is finite or not. Okay, so some very, very basic concrete questions that we don't know how to answer. Okay, so let me just give you examples, a very selective and small list of examples of classical theorems, and when the answer is 1, when you know that you can extend without losing the Lifschitz constant, then you can do it one point at a time. So if the answer happens to be 1, it's very rare, but when it does, then if you show that you can always extend to one more point, you can, by Zorn's lemma, extend to everything. So there is what's called the nonlinear Hahn-Banach theorem, which is, well, the Hahn-Banach theorem isn't a triviality, but once you see the Hahn-Banach theorem, the nonlinear version is trivial, it's the same proof. So you just check you can extend one point at a time, and it just works for Lifschitz functions, provided they take values in an infinity. And a much more substantial theorem is that if you want to go from Hilbert space to Hilbert space, you can always extend it. So it's a classical theorem, a very influential theorem of Kirschbaum from the 30s. So these are two situations where the answer is 1, and it happens, it's rare, and this is not the topic that I'm going to talk about. When you want to extend to arbitrarily many points at once and the answer is not 1, you cannot do this one point at a time. You're going to lose it if you start iterating, so you have to find global arguments. And really the father of this type of investigation is a paper of Marcus and Pizier, which started everything. And it says the following, so here's an example exactly of a situation where the extension parameter is infinite, and then you look at how it depends on n, and it says that if you give me an n point, give me p between 1 and 2, and you give me an n point subset of LP, and a function from it going into Hilbert space, then you can extend it, and the Lifschitz constant will grow by at least what's written here, log into the 1 over p minus a half. And I wrote this under the theorem because there's also matching, almost matching up to log-log. We'll discuss this log-log. There's a matching lower bound, but that's actually due to Johnson and Lindenschau's. And a very famous paper of Johnson and Lindenschau's from 1983, which was motivated by the Marcus-Pizier theorem because, well, the answer, so what Marcus and Pizier asked here, the constant that they got here, the dependence on p exploded as p tended to 1. So this was based on, both these theorems are examples, not the only examples of what's kind of common in this area is use of probabilistic techniques. Both of these papers use probabilistic techniques which are very different from each other. This uses structure of p-stable processes, and they just stop being integrable when p goes to 1. So this exploded here. They asked what happens when p equals to 1, and Johnson and Lindenschau's in 1983 proved that it's fine. So from L1 to L2, you indeed get the limit. So 1 over 1 minus a half is root log n. But this has nothing to do with L1. This is true for any metric space. So if you have an n-point subset of an arbitrary metric space and a Hilbert space valued Lifschitz function, you can extend it, and the Lifschitz constant will grow by a factor of root log n. And in this very same paper, they also, so this answered the Marcus-Pizier question, but they also managed to prove this lower bound. And in doing so, to prove this theorem, it's a very clever proof, but it's very simple and short. It relies on the two ingredients that I said before, the Kirchhoff theorem and the nonlinear Banach theorem, with a new ingredient, which is dimensionality reduction, which is the Johnson-Linischauss lemma, which was a lemma intended to prove this for this theorem. What people usually don't look at is the second part, which is the proof of the lower bounds, which is a much harder part of their paper, which involves really substantial ideas. And when I teach it, it takes me 4 classes to teach the lower bound. So there is, and I'm going to say a few words about it. So there are really nice ideas also in the lower bound, and this is mainly going to be the topic of this talk. But as I said, the upper bound is a different probabilistic method than what Marcus Esquizier is a Johnson-Linischauss lemma, which probably everybody knows, but it says if you give me an n tuple of vectors in Hilbert space, you can find a k which isn't too large, and an epsilon. You can find a k which isn't too large, and new vectors in a low dimensional, in Rk, in low dimensional Hilbert space, such that all the pairwise distances are roughly the same. And this, in combination with the Kirchhoff theorem and the nonlinear Banach theorem and some clever diagram chasing, you get a root log n from that. So this is a chance to mention Noga's work and also a major open problem. So Noga is the person who proved that this theorem is essentially sharp. You see, it almost matches up to this log. And this is a good open question. What's going on here? Very nice open question. So even in this basic phenomenon, we don't understand the dependence in epsilon. This is not going to be relevant to the talk because I'm going to be using huge constants everywhere else, and epsilon can be a half throughout everything we discussed. But this Johnson-Linischauss lemma, which was very influential, was just a lemma for this extension theorem. And now we want to say, okay, so a few words about the convex hull, because this will be related to something that I hope to get to in the end. And it's something that I had to think about because of preparing this talk. So you can also define the same thing for the extension parameter question. When the function takes values, is restricted to take values in the convex hull of the image of the extended function is allowed to go into the convex hull of the initial function. And you can ask yourself, in all the theorems that I mentioned and that we'll see later, well, except for the nonlinear Banach theorem, but the extension parameter actually, the theorem immediately gives an extension because it's a probabilistic argument into the convex hull. But you can come up with examples showing that, so you can find Banach spaces such that it will cost you more to extend into the convex hull than if you allow yourself any freedom outside the convex hull. And this has not been published anywhere, but it comes from just looking into the proof of a classical theorem of Linischauss from the 60s. And I just want to raise this question. It's a brand new question, which is what is the correct relation here? So all I know is that it goes to infinity. And that's a kind of an intriguing geometric question that we don't know what to do. But I'll get back to why I'm looking at this later. Okay, so the parameter that I want to discuss and the main open question for almost 40 years already is this absolute extendability problem. And it's the following. So here's a sequence. It's AE of n. It's a sequence of numbers, which it's just defined to be the smallest constant k, such that this holds true. So look, I'm quantifying over everything. So what does this mean, that AE of n is at most k? It means give me any metric space, any Banach space, any endpoint subset of the metric space, any Lifschitz function on these endpoints. You can extend it to the superspace X and lose only the factor k. Okay, so this is a very basic and fundamental number. It is essentially, well, not clear that it's finite, I'll show you in a second, but it's independent of the specific geometry, even though the proofs use the bounds on it use the specific geometry, but it's a number which is independent of the specific geometric situation, and we call the biggest possible k AE of n. Okay? And the main question, which is still open, and I'm just going to show you focus on it today, is what is the asymptotic rate at which is close to infinity. Okay, so any metric space, any bounded space, any endpoint subset, any function. Okay, let's say, and this is a sequence, so depending on n, let me tell you what are the bounds. So, again, all of them had beautiful ideas. So in 1986, Johnson, Lifschitz, and Chapman proved that this grows at most like log n over log n. And this used, so those of you who know, there is a classical extension method of Whitney. So this really used the Whitney extension method together with a twist, which is a beautiful analytic twist which hasn't been used since then. And I think should be used again. But there is a beautiful idea in this proof that somehow is isolated and didn't reappear. And for a long time, I think I and many others believe that log n should be the truth just because it's nice, so we can get a little bit below log n over log n using the method of random partitions that's already over a decade ago by Lee and myself. And I'll show you a formula. So we have Manor Mendel and I have a new proof of this which doesn't involve any randomness, just a closed formula, and I'm going to show it to you in a second. But the best known, let me just tell you what this talk is about. The best known lower bound is this theorem of Johnson and Lifschitz. And what I'm going to show you today is how to get rid of this log-log, but mainly why this log-log is actually important. So there is a conceptual issue there. But before that, let me just show you, this is the best known bound. And here is the formula. So this is unpublished yet. This is Manor Mendel and I. So I don't know if you can, the shadow is falling in a funny way, right? So tell me if you can you see it? Or? So here is the situation. You have S is a subset of a metric space. Little f is the function that assigns, it's a finite subset, an endpoint subset. Little f is a function that assigns to every point in S a value in the bounded space. And the extension will be defined to be an extension. And if you take a point in the complement, here's the closed formula. So little f is defined only over the subset, so you're allowed to plug elements of the subset in little f. So you sum them up, sum a and s, with this geometric parameter. So there's a normalization factor. M is a parameter bigger than 1. And what you do is you integrate the R over R, this is making it scale invariant, of, so I want to know if we have a point X outside the space. Think of S is here below, this is X. So X, you draw a ball of radius R around X, but R is bigger than the distance from X to the subset. M is a number bigger than 1. You count how many points are in here, it's not empty. Normalize this, integrate the R over R in this range, and the theorem is that for every n, the Lifschitz constant, the minute I wrote it, anybody here can just write this down and play with the triangle inequality and we'll figure it out. Okay? It's a closed formula. But the theorem is that this capital F has Lifschitz constant at most this formula, m plus log n over log n times the initial Lifschitz constant. So the best n is log n, and you get indeed log n over log n. And this comes from an understanding of what a log n over log n means. So it actually solves a different extension problem, for which we now know that this is sharp, and I'll get to this in the end. Okay, but initially the proofs of these used a probabilistic argument that they didn't give a closed formula or give anything so short at least. Okay, so what I want to discuss is getting rid of the log in the denominator. So these are the best known bounds, and this is where we stand today. And there are arguments, I don't know what really belief in mathematics, how important it is, of what should be the truth, but I lean towards this being the truth for various reasons, and some of them I will say. But this is just, anything can happen. But what is true, because there is a conceptual reason why root log n should be the truth, the Johnson and Lifschitz paper dedicated most of the paper was for the lower bound, and a big part of it was why they could not get rid of this log in the denominator here. The second way to discuss it, which I'm going to sketch today, is that there's a real reason is why this is not a purely technical issue. Usually getting rid of log feels technical. Here it's not technical, and I'll explain to you. The 3 dots here are involved notation that would have been clear in 2 slides, but I couldn't include here. But I'm not hiding anything. It's just a notation. So what's really going on? So their method, which is a very influential method for proving lower bound, is a method of reducing the question to studying projection constants, to the linear theory. So here is what they proved. And this is non-trivial, and it's many nice steps. It says the following. Suppose you have a Banach space X, and Y is a k-dimensional linear subspace of it. Okay? So you have this Banach space, and inside there is this k-dimensional subspace. Now look at the unit ball in the subspace, and look at an epsilon in the unit ball. Call it an epsilon. So this is the unit ball in the k-dimensional subspace. Okay? And now look at the identity mapping from this epsilon to itself. Now what does it mean to extend the identity mapping? It means that you find a Lifschitz function from the superspace X back into Y, which is the identity on this very dense set. So intuitively, but this is actually, with getting bounds, it's actually a lot of work. They prove the theorem, which is maybe not a big surprise. It says that if epsilon is small enough, and let's say epsilon less than 1 over k squared would work, if you could extend the identity mapping to an L Lifschitz mapping, so L is a parameter, then you could also find a linear projection, so a linear operator from x to y such that p squared is p, and it's the identity on y, whose norm is at most, you lose a constant, but at most a constant factor times the L that you could extend. So if you could somehow extend it from, if epsilon were small enough, and you could extend from, you can find the Lifschitz function from the superspace to the subspace, which is the identity on the net, then there would also be a linear projection with the right norm. Now methods for proving lower bounds linear projections exist in analysis since the days of Banach and before Fourier analysis. There are many, many, many ways to prove lower bounded embeddings, and this brings a lot into play. Okay, so, but in the context, this is one of the reasons why this root is so natural. Is that, well, the basic theorem is the Cadet-Snowball theorem, which says that in the situation I described before, so Y is a k-dimensional subspace of X, you can always find a projection with norm root of K, so this is a very famous geometric theorem. And this cannot be proved in general, so there are bad examples, which they are easy, you can prove them using Fourier analysis. Usually Fourier projections have this property, where you cannot do better. But in any situation where you cannot do better, the Lifschitz constant of the extension is at least root of k by this general reduction to linear mappings. And you know, and this root is the best you can do because there's always an upper bound of root of k in the linear theory. Okay? So now let's just crunch the numbers very quickly. Remember, Y was a k-dimensional subspace, and epsilon was an epsilon net. Let's call little n the number of points. Easy volume arguments. You just check that log of n is up to universal constants k log of 1 over epsilon. The lower bound of the extension parameter was root of k. Solve this, you get that this is at least root of log n over log 1 over epsilon. Okay? And if you remember, epsilon was 1 over k squared, so this is the log n over log n. That's where it's coming from. So if we want to get the root, that should be the truth if you have this analogy from the linear theory. And a lot of the nonlinear theory developed by analogy to the linear theory. So it's screaming at us. What should we do? We should get epsilon, make epsilon be a constant. Right, this is our enemy here. Okay? But this is a real issue. You cannot get epsilon to be a constant in this strategy. So if we want to get epsilon to be if we want to get the lower bound, we need to get epsilon to be a constant. But this cannot be done because there is a very easy extension theorem of Benjamini. It's really easy. Maybe I'll show it in the end if somebody asks. It's not a hard theorem. It's a very basic fact, which says that if you have any metric space and a subset of it with the property that the minimum distance, minimum non-zero distance, is at least epsilon times the diameter, then you can always extend and lose 1 over epsilon. This is exactly the situation that we have with an epsilon in the unit ball. So if epsilon is a constant, this is a constant. You're never going to get, you can extend by losing only a constant. So if you want to make here epsilon be a constant, there is an upper bound which is a constant, 1 over epsilon. Nothing is going to go to infinity. Epsilon will have to go to 0 in this construction. So if you want to get rid of this log, you're not going to do this by linearization like this. It's just not going to happen.
How can you put that the main use here of U and the
Root is to get rid of the denominator. I can't see. Oh, you're taking a picture. Okay. I can also email you the slides. Where was I? Okay. So even this 1 over epsilon is sharp. This is a theorem that Manor Mendel and I proved a few years ago. It's really an optimization of a really ingenious idea of calculus. This is absolutely beautiful. So this when you have an easy extension theorem, proving the lower bound for it is hard. And this is a very amazing kind of lower bound that, based on very beautiful ideas of calculus. But even this is sharp, so you cannot do better than 1 over epsilon descending. So the new lower bound, which I want to sketch the ideas behind it, gets rid of the log, but it cannot proceed via reduction to linear projections. And indeed, the proof will use expanders and mean cut max flow, and I'm going to show this to you. So I don't have, unlike the previous things which preceded by analogs to linear theory, I don't have any analogs of what's going to come next in the linear theory. It's kind of really a nonlinear argument. And the root log, the root of the log comes from so when you cut its snowbar, the root came from geometry. And here it comes, the limitation with techniques comes from a completely different reason. So this root appears for 2 unrelated reasons. Maybe this is some sort of evidence that maybe something is going on. But again, it's speculation, and we don't know what the truth is. Okay, so let me explain the cast of characters that we look at. They're all very simple. So there's this operation that we're going to play with, which we call magnification. There's a formula I'll draw. There's a picture in the next slide. But the input is a metric space X, some subset, and a parameter R, a positive parameter R. Now, I define a new metric space which I'll denote X of R of S, which is the R magnification of X at S. So we're going to blow up only the subset. Okay? And there's a formula here. It says the following. So this was the subset S, and it says any 2 distances within S, add 2R to them. If you have a point in S and a point outside S, add R to it. If you have 2 points completely outside, don't do anything to it. Because of this preserved triangle inequality, this is a perfectly good new metric space. What did it do? It increased the distances within the subset, and pairwise distances of the subset are the same. So if you try to construct you try to make a function which is defined only on the subset, be Lifschitz, it's easier for it to be Lifschitz. Right? The Lifschitz condition is the distance in the source, and that's the upper bound. So if I make it bigger, there is more examples of Lifschitz functions. Right? While the minute I extend them, it's just as hard as before. Okay, so this is a very natural thing to try to look at when you want to make it hard to extend Lifschitz functions. It gives you more examples. So that's what I wrote here. But of course there's a trade-off, because as I make R bigger and bigger, I make the minimum distance within here become closer and closer to the diameter. And I already mentioned the obstruction before, that if the minimum distance is a constant proportion to the diameter, you can extend using that proportion. So on the one hand, making R bigger gives me more bad examples. On the other hand, making R bigger makes the Lifschitz extension problem easier. So there is going to be a trade-off, and the root log is going to come from optimizing over this trade-off. It's not going to be the, okay? From the linear theory, from the sharpness of the cut at snowbar. Yeah, from the linear theory, which is Hinching's inequality, or, okay, so it's a completely different root. And this is just exactly your 2 forces fighting, and the root is going to come from that force. Okay, so we're going to balance it, and that's going to be the reason for the root. So it's a really different reason. Okay, so that was the first really simple thing that we're going to do. The other, I need to tell you what the target space is. So we're going to be working with the Wasserstein 1 norm. That's going to be the target metric space. So if you have a finite metric space X, I'm really doing a disservice to this, but this is all I need. The transportation cost of Wasserstein 1 norm space, which I'll denote by W1 of x dx, and sometimes I will just write W1, I will mean W1 of x dx. It's the norm, it's a norm space on Rx0, so all the functions from x to r, it's a finite space, so it's just Rn, that sum up to 0. This is the hyperplane of all the vectors that sum up to 0. And here is the unit ball of the norm. E sub x is just the indicator vector, so it has 1 in the coordinate x and 0 elsewhere. So just look at all the vectors from ex minus ey over dxy, and take the convex hull. Look at this polytope. That's a centrally symmetric convex body. Take the norm coming from this. So this is the Wasserstein norm because of Kantorovich-Rubinstein duality. So it's the same as F is total mass 0, so F plus is the same mass as F minus, and the best transportation for plus to minus by duality is the same thing, but we don't need this in this talk, so you can just think of this polytope. Okay, so that's that is the norm space, the target, the y. And now what we're going to do is we're going to magnify an expander at an appropriate subset with an appropriate parameter r. So let's look at the n-vertex deregular expander. And phi of g is going to be the edge expansion of the conductance. So it's just, for every subset, you look at how many edges join S and its complement, normalized by the total number of edges, that is most, this constant times the size of S over n times 1 minus the size of S over n. And in what we discuss, I'm going to write these twiddle signs. They're actually going to be depending on these parameters, but assume that this is a constant and everything is a constant in all of these things. Whenever I write d sub g, I mean the shortest path metric on the expander. And when I have a subset of the vertices in a parameter r, what I called before x sub r of s, I'm going to call g sub r of s. So it's taking the shortest path metric on the expander, but magnifying it on the subset. We're going to choose a subset. Okay? So there is generally there is this notion of Poincare inequalities with respect to norms or metric spaces. I need, in what will follow, I need a Poincare inequality with respect to the Wasserstein 1 space. Very often it's very hard to prove such inequalities. In this case, it's just to do it by hand. It's not a hard theorem. So it's a lemma. And it says the following. Suppose you have a subset, and you have a function from the vertices of my expander into, what is this? This is Wasserstein 1, this norm space. On the sub, so this is the dimension of this bottom space is the size of S minus 1. But I take Wasserstein 1 with respect to the magnified metric. Okay, so this is a certain norm space. It depends on the subset, on the geometry of the expander, and on the magnification. And it says, the theorem is that whenever you do that, and you look at the average distance between two pairs, as you run over uniformly over all pairs of the vertices, that's at most the average over the same thing over edges. This is the norm in this norm with respect to the convex hull, and the constant is r plus log n over r plus 1. In the end, just if we jump at the end, r will be root log n, so this is going to be root log n here. That's when you optimize at the end. Okay, so here is the poorly extendable function. It's a very obvious one in this setting. It's defined only on the subset. It goes into this norm space which comes from the magnification at the subset, and it just assigns to a point in the subset the unit vector, the standard basis in that point, minus you normalize it so it has total, it sums up to 0, so you take the uniform distribution of the subset. Okay, so this is an isometry with respect to this metric. That's how the norm was defined. So it's one Lifschitz is even in isometry. We're going to use the fact that this is an isometry. And the theorem that I'm going to show you is that, well, I'll sketch, is that if you chose, and the parameters I'm going to choose are optimal, but I'm not going to do the optimization, but if the optimal choice of parameters for this problem gives that any function that extends it has Lifschitz constant at least root log n. The parameters are going to be r is root log n, and s is the size of s will be n over root log n. Okay? So let me sketch. I'll really, I want to give you the flavor, and then we'll end. So okay, so what's the game? The game is we had our initial function f, which was 1 Lifschitz in an isometry. And now we try to extend it, so now capital F is defined in the entire vertex set, takes values in Wasserstein space. And it's L Lifschitz with respect to the magnified metric of the subset. And the goal is to deduce that L is at least root log n. And there's going to be a trade-off. There are going to be two enemies fighting each other. One of them we're going to beat them using the Poincare inequality, and the other one will be other properties of the expander. So let's first use the Poincare inequality. So, okay, so I need to look at what happens to balls, or actually pre-images of balls. So if I have a radius, a number s bigger than 0 in a vertex, I'll define b sub s of x is the pre-image. It's all those y's such that fy is close to f of x in this Wasserstein 1 norm, s close to it. And again, I'm telling you that in the end, the optimal choice will be s is a constant and log n for a small enough constant in the end, but we'll see. Okay. So these are these notions of balls, these are Wasserstein balls. And this is the case one where we're going to use the Banach space value Poincare inequality. So suppose that all of these balls are small. So for every x, there's only at most half of the points are mapped to Wasserstein distance less than s from it. Then in my Poincare inequality, the uniform average over all pairs is at least s over 2. Because for every fixed x, half of the points are distance more than s from it. Okay? And now I told you already, s was a constant times log n, so this is the thing that was smaller in this vector value Chigger inequality. This is going to be a order log n. Now, okay, so I'm just using the Chigger inequality. So that was this term, this log n. And that's bounded by what I said, log n over r was root log n, but times the same average over edges. Over edges, I'm going to do nothing more. This is a discrete gradient, and I'm going to use the Lifschitz condition. So this is from here to here, I just said that capital F is L Lifschitz. And the L comes out, log n over r, and the magnification on a deregular graph, you can just compute it. So the average distance in the magnification over a subset over all x and y, which this is just a combinatorial accounting argument, is equal to whatever is written here. Okay? So in our choice of parameters, which is going to be optimal because of the other enemy, but now I'm just telling you it's already optimal, r is root log n, s is n over root log n, so this is a constant, and you get r l is at least root log n. So this is when the Poincare inequality, but with values in a Wasserstein space, helped us win. What happens if we don't? So this was when all these balls are big, so there is a big ball, there's one ball, which is, there's a point x0, such that more than half of the points are mapped into this ball. So this means that this ball cannot swallow up all of S. So S minus the ball is at least S over 5. This is a short argument, which I'll skip because I want to get to I have 5 minutes and I want to get to the meat of it. But the basic idea is, if this set is big, this is a deregular graph, then its diameter is log its size. So there are 2 points which are far apart. But little f was an isometry on the subset S. So if 2 points are far apart, they're also far apart in the image. And therefore, they cannot be both in a small ball. Okay, so there's a slide here, I'm skipping it, but that's the intuition. If this set is big, there are 2 points which are far apart, log its size. So they cannot all map to a small ball. Because f was an isometry, I'm using the opposite direction okay, so I'm skipping this. Okay, so now I know that the complement of the ball is big, this constant proportion of the set, and the image of the ball itself is big. So there are many edge disjoint paths joining these sets. This is an expander, okay? And it's a constant degree expander. So let's say they start, it's S minus the ball, these are disjoint sets. And here, and I can make the initial vertices be distinct. because it's a constant degree. If I use Menger's theorem and I get many paths starting from here, I can just delete some of them. It's a constant degree. So the picture is, this was a big set, this was a big set, therefore there are many edges join paths. And what I'm going to start examining is what is, okay, so let's give them names. I just want to, so let's say these are the paths, so ZJ1, ZJ2, up to ZJKJ, where the first guy is in S, and the last, S minus the ball, and the last one is in the ball. Okay, I just need this notation. And I'm examining, what's written here, so I'm taking 2 points, 2 initial points, two of these paths, and I look at the distance between the first point and the last point. Where is the last point? Well, let's say this point and this point, and this point and that point. If I sum these 2 guys up, you can see this in the picture, then, so in the image, these points are, well, S is a big set. So these points are going to be far apart, and little f was an isometry. Remember, the zi's were in S, so f was an isometry here. So these points are far apart in the Wasserstein space, and by design, the endpoints are in a small ball of radius S. So these 2 must be far apart, because you can say that this distance plus this distance, the triangle inequality, is at least this distance minus this distance. So that's the first inequality. And then you just write a formula for what the magnification means, and you get it. So this is very close to this. So anyway, this is a tiny computation, but the triangle inequality is what's hiding behind it. And you get that if you take 2 points in here, their distance in the image is at least the graphmetric minus this parameter. And if when we average this, C is small enough, we just get that the average distance between the first point in the path and the last point in the path is this log the number of paths, which was log the number of points, minus something which I can make smaller. So the whole thing, this average distance is at least log n. Provided C is small enough. That's okay. So I took the first point in this edge joint path minus the terminal point, and the average distance I got was roughly log n. But I can bound this path by the triangle inequality along the path. In Wasserstein, this is actually unmetric in the image. So I can break this path along each of these paths. I can break this from above as a sum of increments along edges. But all these edges are distinct. So I can bound this from above by the sum over all of the edges, and this by the Lifschitz constant. Which again, the sum over all the edges I can compute, and M was the size of S. In our parameters, D was a constant. M was the size of S, and I told you the size of S was N over root log N, so this becomes L over root log N. And before it was bigger than log N, so for a completely different reason, using expansion again, L is at least root log N. Okay, and so this is very different from projections, and just in time, so I'll stop here.